Good afternoon. It's wonderful to be here. It's wonderful to get to present to all of you. Before I get started with this final presentation of the session, and I'm grateful that all of you stayed around, can I ask a question by a show of hands? Please put up your hands if you are a potential end user of quantum computing, someone who works in industry, who wants to use quantum computing for your work to gain some strategic advantage. Is that you? Now, can you please put up your hand if you are an expert in quantum computing? If you build quantum computers, if you are an expert researcher, put up your hand. There's only a few. That's good, because this talk is not for you. This talk is for everybody else. The objective today is to share with you some insights, sometimes deep, dirty secrets about quantum computing, to help you actually gain advantage from this field. And I'll tell you today about the work that we do at QControl on making quantum computing useful with the world's first performance management software solution. For those of you who are not familiar with QControl, we build AI-powered infrastructure software to make quantum computers useful. When I say AI, I don't mean a ChatGPT wrapper. I really mean building new algorithms and agents to solve some of the fundamental problems that we've heard about today, problems of error and hardware instability. We connect at the low level to the control electronics from our friends at Quantum Machines and Q-Blocks and others, and at the high level to the algorithm frameworks for development and the developer tools from Classic, from Strangeworks and others, that allow you to write your programs. We provide everything in between, telling how the hardware should actually be manipulated. Now, at this point, QControl is 5.5 years old. We are the only company in the sector with a track record of delivering products in software and ensuring that they are useful for advancing the quantum computing sector. We have delivered and demonstrated on real hardware 10x enhanced capability, deeper circuits run on real hardware, 100x cost savings to end users, and over 1,000x performance enhancement in real algorithms run on real quantum computers. We work with national laboratories around the world. We work with effectively all of the major providers of quantum computing hardware, teams that build devices. We announced in May that our software that I'll tell you about in a minute will run natively on IBM's hardware and all of their future machines. And of course, we work with academic organizations as well. Now, the reason we're all here, or at least the people who put up your hands, is that the Boston Consulting Group has identified an $850 billion market opportunity associated with the application of quantum computing in a variety of areas. Now, you've heard all about these different areas through the talks today, so I will not belabor them. Suffice to say that whatever your area of interest, from machine learning to finance, may be, you're all hung up on one problem. That is the fact that the hardware is unstable. That when we put information into a quantum system, over time, that information is randomized. It is lost. And that randomization of information results in computational errors. That is the one problem that is preventing all of you from having a share today in that $850 billion opportunity. Hardware error is blocking all of the benefits that we know these systems can, in principle, deliver. This is a dirty secret. What does it look like when you, as a user, run an algorithm on a quantum computer? In this graph on the top, I'm showing what you should get for an algorithm. It's called Grover's search algorithm, if you're familiar with it. It's a needle in a haystack, unstructured search. You should identify the location of a marked state, of the needle in the haystack. When you actually run this on a real machine, you get the bottom. It's a random output. The correct answer is not identified by the algorithm. It's not even in the top 5 most likely outcomes identified by the algorithm. This is the user experience that all of you have. In addition, we hear a lot about scaling. We hear about making quantum computers bigger. We hear about metrics like gate fidelity? What is the randomized benchmarking fidelity? But the reality is again different. Those two lines on the top, on this logarithmic graph, represent the capacity, the in-principle power of the hardware. For the experts in the room, they come from randomized benchmarking. What is the predicted success of an algorithm? The black and the gray are what you actually get. And I will remind you, that is a logarithmic axis. Every tick mark is a factor of 10. This is like a 10,000-fold gap between what a user actually experiences and what the hardware could, in principle, develop or deliver. This is a major challenge for end users. Now, to address this kind of problem, there's been a lot of effort in our community over decades to develop techniques to deal with error. We just heard in Steve's talk about quantum error correction. Quantum error correction is a technique that's used to encode information and spread it out in space in order to gain resilience against error. It's an algorithm. It's very complicated. It doesn't work right now. It does not make things better because it is so complicated. It involves so much overhead. In the near term, teams at IBM and elsewhere have pioneered something called error mitigation. This is post-processing. Run the algorithm many, many times, and then combine the answers in order to help see through the noise. There is a third way, and that third way is something that QControl specializes in. This is called error suppression, where we effectively build a force field around the individual quantum logic units, the qubits, in order to give them resilience against the sources of noise and error in reality. This is what I'll mostly talk about. But no matter which of these you're interested in, all of them require typically expert-level configuration. You must be an expert in either error suppression or error mitigation or error correction in order to actually implement these things in any way to gain a benefit. All of us, as we try and put quantum computing to use, have been stumbling around in the dark, searching for insights from real quantum computers. And we're very excited that we've been able to change that with a product that we released at Q2B in Silicon Valley last December called FireOpal, to help you see the light in the dark. FireOpal is a zero-config performance management solution. It is complete, and it automates all aspects of reducing error in quantum computers such that you as an end user only need to focus on your algorithms and then the answers that matter to you. Everything else is abstracted away through our performance accelerating infrastructure software. It connects to supported backends via IBM and AWS, and we've been very happy to work with organizations like Capgemini, Park, and Quantient to put this software through its paces. What does it deliver? Well, remember the problem that I showed you before, the noise, the random output from a machine. With FireOpal, you get the answer on the bottom right. These are real data taken from a real quantum computer, and they're indicative of the fact that this is a binary transformation. The machine goes from giving useless output to giving you the right answer. The likelihood of getting the right answer increases more than 1,000 times, depending on the individual algorithm being studied. For you as end users, there is no overhead. You don't have to write any configurations. There are no code blocks to copy. There's not even any extra work, no post-processing to be done, no extra repetitions or shots. All you do is execute one line of code and achieve maximum performance. Behind the scenes, there's an entire complicated workflow that is expert configured by the team at QControl and completely automated by FireOpal. This starts with depth-reducing compilation, error-aware hardware mapping, circuit crosstalk elimination, optimized gate replacement. We completely redefine the machine language used on the hardware. All of these things would typically be the topic of a PhD. But for us, it is delivered as one line of code, fireopal.execute, for you to operate with any algorithm of your choice. When you use this, you're able to recover all of the lost performance that is effectively hidden by noise and error. It is latent performance in the hardware. This was the same graph I showed you, the gap between what the hardware could provide and what a user typically experiences. And you see that with FireOpal, we recover more than 1,000x to be within a factor of 2 of the best the hardware can deliver. And since this graph was taken, it's in a published manuscript, we've gotten even closer to the absolute ideal from the hardware. But we've taken that approach of simple, no configuration, zero config, execution of algorithms on real hardware, and we've extended it to hybrid algorithms, algorithms like QAOA, where again, the complexity of setting up the execution of a hybrid algorithm can now be completely abstracted away. And with one line of code, you can get the right answer. With a simple example from quantum machine learning, you can see the difference that adding this single-line execution of QAOA delivers. The top is the set of outputs that the machine should give, in the same spirit of what I showed before. That's what the output should look like, finding the answer to what's called a max cut problem. On the bottom, what you see alternating is between right now the default and what you get with QControl. When you run the default, you get random outputs. You get a uniform distribution across all the different possibilities, as you see right here. But adding that one line of code, solve.qaoa, changes that random output into the right answer. No configuration, no settings. Across all applications, the benefits are enormous. A factor of 1,000 improvement in Bernstein Vasani. Actually, 9,000x was the largest we've measured. More than 200 times in quantum Fourier transform. For those of you who know about this algorithm, it is a very deep algorithm. It has many gates. More than 200 times improvement in the execution of QAOA, quantum approximate optimization algorithm. These benefits persist across these and many other applications and are all achievable by you without having to know anything about what's happening inside the box. Now, we're very excited to announce something this morning, bringing this capability, this value, closer to all of you in Japan and, of course, in the UK. We announced a partnership with our friends at Oxford Quantum Circuits, connecting this kind of infrastructure software to their very unique approach to building superconducting devices. And, of course, OQC has a partnership with Equinix in Japan, bringing this capability onshore. In our earliest benchmarking demonstrations, we have shown that with our tooling, we can immediately improve the performance of the so-called logic gates, the building blocks of quantum algorithms. Right out of the box, more than 5x improvement in those elements. But when we start to put these together to run algorithms, the benefits really become extraordinary. Comparing the bare metal performance, the baseline of what you get for an algorithm called Bernstein Vasani as a function of how many quantum bits you're using in your circuit, is the black, that's the bare metal. But when you combine OQC with QControl, you see the boost to the purple. Over 140 times more likely to get the right answer in an 8-qubit circuit than the bare metal alone. Entirely achieved with software. And these are really only our initial benchmarking experiments. We think there's even more to come. All of this accessible to you on OQC's Lucy system using our infrastructure software. Results like this are what led Julian Van Velzen to say, in the years ahead as we move closer to quantum advantage, FireOpal will enable real applications to deliver value sooner. Julian is from Capgemini and has worked with us on a variety of applications in quantum machine learning, even comparing the performance of our infrastructure software against packages for, say, error mitigation, and showing that FireOpal consistently delivers superior performance with no code and no configuration for the end users. Ultimately, our objective is to make this kind of capability in quantum computing useful to as wide a range of users as possible. This is not just a tool for experts. It's not just a tool for people with PhDs. This is a tool that delivers performance, value, and simplicity so everybody can benefit, whether you're an enterprise, whether you're a researcher, whether you run a small business looking to take advantage of quantum computing. Our focus has been on making this kind of capability useful to as broad a range of users as possible. If you are interested in putting this technology to work, please get in touch. With this QR code, you can link to Opal. It is free to use. You can run this immediately, connecting to supported backends. We will be supporting a wider range of hardware providers in the next few months. As I mentioned, this software will run natively on IBM machines starting from late this year. And please reach out to me or my colleague Arvind, who's here as well, if you'd like to learn more about how we can make quantum computing useful for you. So let me thank you very much for your attention, and I'll take any questions.
Does anyone have any questions? どなたかご質問お持ちの方いらっしゃいますでしょうか？手を挙げていただければと思います。Please raise your hand. Yes, gentlemen, way to the side. Thank you.
Yeah, thank you. It sounds fascinating. At the start of the talk, you said very vaguely, I think, that it reduced computer costs by a factor of 100. What's that in dollar terms?
That's a great question. The question was about how this factor of 100 manifests for end users in dollar terms. So that factor of 100 comes from a couple of places. It comes in one part from the fact that error mitigation, which is commonly used to reduce the impact of errors, IBM has used this in many of their recent publications, it involves running the same circuit over and over and over again with small changes and then processing the results of all those different variants in order to see through the noise. Typically, you have a factor of 100 to 1,000x overhead in circuits. The technology that we deploy is deterministic. That means in one execution of the algorithm, the noise is suppressed. There is no post-processing. There is no repetition. So in one example, we compared two different providers, some simple, smaller devices that come from IBM against a premium backend from another provider. And here, by adding this deterministic error suppression, which doesn't add any overhead, there's no additional compute time, we were able to make the two systems indistinguishable up to the size of the system, up to the hardware limits. The cost differential between those two machines per second of execution was 400x. So running an optimization algorithm for machine learning would cost about $250 on the IBM system and $89,700 on the alternative premium backend. That's enough data to write one short manuscript, right? Factor of 250 versus 89,000. That is an enormous cost saving for the end user that's facilitated by this technology. Thanks for the question.
Great, excellent. Any other questions? Yes, let's see one more person there.
Thank you for the great talk. In future, do you think there's potential for a combined approach using suppression, mitigation, and correction?
That's a fantastic question. I talked about these three approaches. Error suppression is great today because it deterministically reduces the errors. We know you can push right up to the so-called T1 limit, the incoherent error limits in the device. We have shown already that combining error suppression with error correction, actually running error correction, increases the likelihood that the error correction algorithm correctly identifies the location of the error. So that's in our published work. But error mitigation in the interim also has some opportunities, because error mitigation can help address one kind of error that error suppression cannot fix. That is a T1, an incoherent error, when your qubit spits out a photon of energy. It's like coral bleaching event. It just inverts itself and it dies. That is not something that error suppression can fix, but combining error suppression with error mitigation can give you a way to suppress those T1 errors in the intermediate period and also reduce the overhead required for error mitigation. You can do less mitigation and rely on the combination of the two. So all of them fit together. They're all complementary. I don't want to give anybody the idea that this is one or the other, but in sequencing, we believe error suppression must always come first. You should always stabilize your hardware as much as you can, and then things that cost more in terms of time and devices can be added on top.